So as usual, welcome to this session of the Discrete Maths 2 course. As we announced last time in the trailer for today's session, today we are going to complete our journey to infinity and beyond. That is to say, we are going to, more precisely, study what it means for two infinite sets to have the same number of elements, whatever that may mean. And we will see that that's the key to answering the question that motivated us in this journey towards infinity. Namely, can an ideal computer, a computer, yes?
We are going to infinity and beyond. Does that mean we're going where no mathematician has gone before?
So the question is, does it mean that we are going where no mathematician has gone before? Actually, we are going to explore a small part, a very, very tiny part of a landscape where mathematicians have gone long before us and where they're still going. If you're interested, then you can start exploring large cardinals and mind-boggling things you would never even have dreamed of that existed. You'll be like the replicant in Blade Runner. When he says, I've seen things that no human will ever see. But then hopefully the end will be better for us than it was for the replicant, at least for the time being. Okay, before we actually start doing that, it's important to get our neurons buzzing, as I always like to say, and also to firm up our understanding of two important, very basic, but very important concepts about functions. Unfortunately, Dr. X is with us today, at least in spirit, not in slides, asking us a couple of questions about functions. Okay, so suppose that I have a function f here that goes from the integers to the natural numbers or non-negative integers, if you prefer. And this function f is defined as follows. It takes some integer x as input, and it returns x if that integer is non-negative. Otherwise, it returns minus x. That's a well-defined function because it takes any integer to a non-negative integer. In fact, if it's negative, it flips the sign. Questions for you from Dr. X. Is this function injective? Of course, to answer this question, we need to know when a function is injective, which is something that you saw a long time ago last semester, and probably even before. But there was a previous life, so it's always a good idea to refresh our memory from previous lives. So this should be like déjà vu for you, something you've already seen, but when you see it next time, it looks like it's the first time, even though, I mean, you've seen it before. So a function is injective when, and I'm sure all the people watching the lecture online are actually answering now, they are saying that the function is injective if it keeps distinct elements distinct. That is to say, if you take f of x and f of y and they are equal, then x must be the same as y. That's what injective means. So your colleague is saying, well, that's not injective. So that's what this means. Is this true? And your colleague is saying, well, no. For example, this function maps 1 and minus 1 to 1. And 1 and minus 1 are not equal. If you have 1 krona, it's better than to have minus 1 krona, because then you owe it to the bank. Okay, this function is not injective because it takes two different things. In fact, That's an example of the many different things that the function banks into the same place. So f of 1 is 1, f of minus 1 is also 1, but 1 is not the same as minus 1, so the function is not injective. It doesn't keep distinct elements distinct. That's what injective means. Oh, by the way, did you see this in discrete maths 1? Because I assume you have. If you haven't, I'm going to go upstairs afterwards and sort of spank a few bottoms. Metaphorically speaking, of course. Okay, so is this function instead surjective? Now, this is not a swear word. It means what? It means that every element of the codomain, that is to say, in this case, n, is actually the image can be reached by applying f to some element of the domain. Everything in n is actually f of some integer. Is this true? Sure, it's true. You take any n, it's actually equal to f of n. So you can reach everything in n. The function maps, sort of the range of the function is the whole codomain. You don't leave anything untouched. So the answer in this case is yes. Okay, so let's look at another example, just so that we know what we're talking about. So let's instead assume that I have a function g that goes from n to z. It goes the other way around, and we define it as g of n is equal to n. It's the identity function. I take n as input, I return n. I'm sure even I could code this one in your favorite programming language, modulo compiler errors. Okay, so is this injective? Yes, sure, there are no tricks there. If you take two different numbers, like 3 and 35, they will be mapped to 3 and 35, so they are distinct. Is this surjective? No, it isn't. You cannot get any negative number that way. You can only get the non-negative ones. So it's not surjective. It doesn't touch all of the negative ones. Negative numbers are not the image of anything. So pictorially, so here we have our n, here we have our z, 0, -1, -2, and down the spiral like Alice in Wonderland, then that's the part that you can get. You get up to here, that's where actually G goes. You cannot get any of the negative numbers that way. So that's injective, but not surjective. Now, a bijection is a function which is both injective and surjective. Basically, a bijection is a one-to-one correspondence between the two sets, which are the domain and the codomain. And that's a fundamental concept for today's lecture, because that's the tool that we have to measure when two infinite sets have the same number of elements. That's Cantor's definition of when two sets have the same elements, namely when there is a bijection between them. And that's exactly where we left off last time around. Two functions have the same, two sets have the same cardinality when there is a bijection between the two sets. A function that takes different elements and leaves them different, and moreover, it hits everything in the target set, B. Okay, so here's an example of a bijection over two finite sets of size 4. However, since when you have an infinite set, you cannot really start counting how many elements there are. You will never terminate. And it's not even clear what it means to count how many elements there are in an infinite set. This is the definition that actually extends naturally to measuring the size of infinite sets. Okay, so this is our mantra for today. Two sets A and B have the same cardinality, have the same number of elements, if you can construct a bijection between the two sets. A function that keeps elements distinct, distinct elements distinct, and covers everything of the target set. Okay? Any doubt about this? Because what we are going to do now is to use this tool to explore infinity. Let's start with something that, in fact, we have already seen in some way. Not quite, actually, but a version of this. Let's take two infinite sets. This is like a boxing match. On your left, there is the set of the natural numbers, 0, 1, 2, 3, and so on. On your right, there is the set of the even numbers, 0, 2, 4, and so on. Question: do these two sets have the same cardinality? Shall we let them punch each other to death to figure out who wins? And if nobody wins, then they have the same cardinality? Well, I asked Dr. X, actually, before coming here, and he said, come on, Luca, no way. No way. The integers are bigger, the non-negative integers are bigger than the set of all the even numbers. In fact, the set of the even numbers is a strict subset of the set of all the natural numbers. So how can they possibly have the same cardinality? And here's an example. I mean, I give you the obvious function. F of x maps to x. That's a function that goes from the even numbers to the natural numbers. It's injective, but it's not surjective. It leaves out all the odd numbers. We cannot get to them. Is Dr. X right? Oh, your colleagues is saying, one of your colleagues is saying, no, he isn't. In fact, he's not right. The two sets have the same cardinality. Even though one, the set of the even numbers, is a strict subset of the set of all the natural numbers, the two sets have the same cardinality. There is actually a bijection between the two sets. Now you may say, oh, what is this bijection? Well, let's work it out together. What we want is a function f that goes from the set of even numbers to the set of natural numbers. And this should be a bijection. Okay? So what is this function? Your colleague is saying divide by 2. So f of 2n goes to n. For every n greater or equal to 0. Let me depict this pictorially for you. Here we have the even numbers. And forgive me if I don't write them all. And here we have the natural numbers. And again, I will not write them all. What does f do? It maps 0 to 0, 2 to 1, 4 to 2, 6 to 3, 8 to 4. And when you picture it this way, it's clear that this is a bijection. Why? Because no two numbers, no two even numbers get mapped to the same natural number, because 2 times n and 2 times k can only be equal if n is equal to k. And moreover, it's a surjection. Why? Well, because you can double every natural number, and then when you divide that number, you get the natural number you started from. So any number is half of an even number. Okay? Surprise, surprise. In the world of infinity, okay, when you work with finite sets, if A is a strict subset of B, then obviously A has fewer elements than B, because there is something missing. But when you move to infinity, it doesn't really mean, this does not imply that A is smaller than B. The two sets may have the same number of elements. Hello? Any sign of life out there? Well, I can see that people are doing all kinds of things. Come on. Any doubt with this? Of course, it may look odd. But how about the reasoning? That's the only thing you should focus on. Thou shalt leave behind anything that you call intuition when you move to infinity. Because if you carry your finite intuition with you, you're lost right at the beginning. Thou shalt use, that's the second commandment. When Moses comes down with the infinity laws, the second commandment is, thou shalt use the definition of what it means for two sets to be equivalent, to have the same cardinality. Namely, there is a bijection between them. If one exists, they have the same number of elements. They have the same cardinality. And in this case, lo and behold, here's the bijection. So the even numbers are as many as all the natural numbers. Any doubt about the fact that this is a bijection? Shouldn't be. If there is doubt, think about it or ask questions. Oof. Now, if you're confused, don't worry. If you're in doubt, if this looks odd, don't worry. You're not the first one, and you won't be the last one to be confused. If you don't take my word, listen to Jorge Luis Borges. How many of you have written books, have read books by Jorge Luis Borges? Lift your hands. If you haven't, go and buy one or steal one from the net. Sorry, he's dead anyway, so he doesn't, perhaps he has hairs to his copyright. Read The Aleph. It's a book about infinity. So it's a novel, sorry, it's a short story in a collection of stories about infinity, where there's this guy who's lived infinitely long. And you know, if you live infinitely long, it's not strange that you have written Hamlet, or you have done everything that humankind has done so far and more, because you have infinite amount of time. You can do anything in an infinite amount of time. Even monkeys could write Hamlet, so can you, so can I. And it goes on saying, well, there is one concept that corrupts human mind, everything that we do, and it's infinity, it's not evil. Evil is a puny little concept that only has to do with ethics, which is an important thing, but infinity is much more corruptive. And remember, Moses' commandment number 1, don't trust your intuition. 99% of the time, it is wrong. And actually, I'm underestimating the amount of time that it is wrong when you're dealing with infinity. Use the definition. Because we've only seen the beginning of something which is going to look much weirder from now on. Okay, so we'll look at the even numbers. How about the integers? We say that before we look at the integers, let's look at the definition. We say that the set is countably infinite if it has the same cardinality as the set of the natural numbers. Countably infinite means that its infinity can be counted. Because if you can put it in a bijection with the natural numbers, it means you can say this is the first element, this is the second element, this is the third element in your set, and so on. You can enumerate them one after the other. That's what a bijection does for you. It tells you who's first, who's second, who's third, and so on. Now, how about the set of the integers? Is it countably infinite? I asked Dr. X, and he said, come on, come on, come on. You convinced me that the set of the even numbers is the same size as the set of the integers, of the natural numbers. But the set of the integers goes to infinity in two directions. It's bi-infinite. It goes to infinity in the positive sense, and it also goes to infinity the other way, where the snow is today. Well, that's intuition. We are not talking about intuition. We are talking about bijections here. That's the only way to figure out whether the integers are the same size as the natural numbers. And you know, Dr. X also said, okay, if I try to enumerate the integers, I will start. I can start like this: 0, 1, 2, 3, 4, 5, 6, and so on. But in this way, I will never get to enumerating all the negative ones. Does this mean that you can't enumerate them? And you know what? The answer is no. You can enumerate the integers. And the way to do it is to do something that computer scientists know how to do very well. It's something which is called round robin or interleaving, round robin scheduling. When you will be doing operating systems, you will learn about this. But we are going to apply it in a simple-minded way to enumerate the integers. And following Katy Perry, this is how we do it. Okay, so on the first line, you see the natural numbers on the slide. On the second line, you do see the integers. So how are we going to enumerate the integers? We do it as follows. We start from 0, and then we say, positive numbers, take a step. 1 comes along. But then we say, now it's your turn, negative numbers. Take a step. -1 comes along. And then we say, noblesse oblige, positive numbers, take a step. 2 comes along. And then we say, now it's your turn, negative numbers. We don't want to discriminate the negative numbers, so we let them come one at a time. It's like when you have 2 long queues, you merge them together to form a one orderly queue in exactly that way. And what happens? Lo and behold, you have enumerated all the integers in a bijective correspondence with the natural numbers. And now, what is this bijective correspondence if you had to express it as a function? I've expressed it as a sequence here, but this sequence is really hiding a bijection. Actually, it doesn't hide it particularly well, so let's see what it is. So here we have the natural numbers. Okay, here we have the integers. 0, 1, 2, 3, 4. And here we have 0, 1, -1. What am I saying? 2, -2, 5, 6. 5 goes to to 3. And this goes to -3. And it keeps going. So what is this function? Okay, I want a function that corresponds to this enumeration of the integers. It goes from n to z. How is it defined? Okay, so your colleague is saying If n is equal to 2k, say, that is to say is even, then what we're doing is we divide by 2, so we get k, and we take the minus of that. Okay, so 2 goes to minus 1. Why? Because 2 is 2 times 1, and we take the minus 1. 4 goes to minus 2, because 4 is equal to 2 times 2, so we take minus 2. 6 goes to minus 3. So you divide and then take the minus of the result. Divide by 2. And what about the odd numbers? Let's look. 1 is equal to 2 times 0 plus 1. It goes to 1. Okay, plus 1. 3 is equal to 2 times 1 plus 1. It goes to 2. Okay, plus 1. And so on. And you can check that this works for all of them. But in any event, that's just the mathematician's view of things. If you look at the sequences there, it's absolutely clear that if you do things this way by using the interleaving method, you actually produce an enumeration of the integers. It's an enumeration that covers them all. It doesn't leave any integer behind, and it puts them in correspondence with the natural numbers. So the integers are also a countably infinite set, even though, unlike the natural numbers, they are infinite in 2 directions. Now, I realize that this can be weird, but don't worry, it gets even weirder. The only way, yeah, I mean, screams of excitement here in the audience. I'm sure that people are committing suicide at home. No, I hope not. I hope not. Far from it. You should get really excited because it gets even more exciting now. It gets even more exciting. Well, when you travel up the number system, the next guys that you meet are the rational numbers. Now, do we all know what the rational numbers are? The rational numbers are the fractions. 1/2, 3/2, 1/3, p over q, where p and q are integers. Those are the fractions. Those are called the rational numbers. And now a good question that we can ask ourselves is, well, given the topic of today's lecture at least, is, well, is this set countably infinite? Can the rationals be put in correspondence with the natural numbers in a one-to-one correspondence, a bijective correspondence? And you know, I always ask Dr. X, and he told me, okay, Luca, you convince me that the even numbers are countably infinite. That's okay. I can take that, sort of. You convince me that the integers, the whole integers, both positive and negative, are a countably infinite set. There was a punch in the stomach, but sort of I'm still standing. But come on, the rational numbers are a totally different ball game. They are dense. What does this mean? It means that unlike the integers, unlike the natural numbers, if you take any two rationals, there is always a rational in between them, which means inductively that between any two rationals, there are infinitely many rationals in between. How on earth can you list them all? Well, you know what? I call Pikachu. In this case, Pikachu was Cantor, who actually proved in 1874 that the two sets, that Q, the set of the rational numbers, is countably infinite. And you know what? If this sounds weird to you, rest assured that it was even weird for him. After he proved this theorem, he wrote a letter to Dedekind, another very famous German mathematician, For some reason, they wrote to each other in French, even though they were both German. And Cantor wrote to this guy, "Je le vois, mais je le crois pas," which means I see it, but I don't believe it. And he had just proved the theorem. He went through over it a zillion times, and he was convinced that it all worked. And you know what? In fact, the proof is something that you can pictorially understand in 1 minute. Let me show it to you, or try to at least. And if I make mistakes, you will correct me. In fact, I'm going to show you something that on the face of it looks a little different, but in fact, it's exactly the same. In fact, it's more. Now, remember, a rational number is nothing but something of this form, P over Q, when P and Q are integers. Well, there are, of course, special cases. You don't want Q to be 0, for instance. And many of these pairs of, because division by 0, last time we looked at it, was not allowed. That's the only reason for not considering Q equals to 0. So let's do it. And moreover, there are lots of these pairs of integers that actually represent the same rational. So for instance, 4 over 2 is the same as 2 over 1. At least last time we looked at it. So there is a lot of redundancy there. But anyway, let's look at pairs of integers. Well, what are pairs of integers? Well, we can represent them as integer pairs in this beautiful Cartesian plane, which you're all familiar with since you were born, essentially. Okay, so this guy here is the point 0, 0. This one is the point 1, 0. This one is the point 2, 0. This is the point 0, 1. This is the point 1, 1, and so on. And you have all these integer points here, which I'm not going to name because I'm lazy and because the picture gets cluttered very quickly. Now, it looks like there are a hell of a lot of points in there. You go 4 quadrants, each one of them filled with an infinity of points. Now I'm going to show to you how you can actually enumerate all these points and put them in correspondence with the natural numbers. And you know what? It's easy pictorially. You can do it in many different ways, but for instance, you could do it this way. You start traveling, 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 traveling. I'll stop here because I don't want to go to infinity. It's a square spiral, absolutely, as your colleague is going. And you know what? If you keep spiraling long enough, you will hit any point with integer coordinates. So, spiraling infinitely long, you hit them all. That's why I call this the Pikachu proof. Collect them all like the Pokemon. I mean, you're probably too old for that. You never had to play Pokemon with your sons or daughters, but at some point, perhaps they will come back in fashion. Yeah, okay, some of you are still playing Pokemon. Fantastic, fantastic. I thought nobody was going to come out. So this is called coming out. It's called the Pokemon coming out. But anyway, I really appreciate the fact that people are still out there playing Pokemon. I had students in Aalborg who were collecting Pokemon cards and playing Pokemon where they were supposed to do exercises for one of the courses I was teaching, but that's a different matter. But what is the bottom line? The bottom line is that you can enumerate all the rationals because, in fact, you can enumerate all of the points in the two-dimensional plane with integer coordinates. And the rationals are a subset of those. We've enumerated more. So believe it or not, Cantor was right. Q, the set of all rational numbers, is countably infinite. Woo! So let's summarize. The even numbers are countably infinite. The natural numbers are, of course, countably infinite because they can be put in correspondence with themselves. The integers are countably infinite. The rationals are countably infinite, even though they are dense. Between any two rationals, there are infinitely many other rationals, whereas in between any two consecutive natural numbers, there is none. Odd as it may seem. I know what you're asking now. Is everything countably infinite? Because, I mean, it looks like it by induction. 1, 2, 3, that's good enough for me. Everything we've seen so far is countably infinite, so by induction or by guessing, extrapolation, whatever you want to call it, everything is countably infinite. Well, well, well. Have you ever heard about the Hilbert Hotel? You've never heard about the Hilbert Hotel? Fantastic, because this gives me the opportunity of entertaining you with some, before the break, scientific theater. And in fact, there are theater pieces which are based on this idea of the Hilbert Hotel. A very famous theater director in Italy, Luca Ronconi, who happens to be called like me. Actually, I'm called like Luca Ronconi, but that's another matter. It's symmetric, so we have the same name. He actually staged in one of the major Italian theater, a theater piece written by a British mathematician slash physicist, John D. Barrow, a play about the infinite. And what is the idea of Hilbert's Hotel? Suppose that you have a hotel, take Hotel Natura, and all the rooms are full. You're a guest, you're a tourist, or somebody who wants to spend the night at the Hotel Natura. You go there and you say, do you have a room for me? The answer is going to be, no, we are fully booked, sorry. Come back next year or whenever you have rooms. Okay? But this has got everything to do with the fact that Hotel Natura down there is a puny little hotel with only, say, 644 rooms. I don't know how many rooms there are. I'm just making it up. Or 1,034 rooms. What if the hotel had infinitely many rooms? And we index these rooms with the natural numbers. And these rooms are all full. Suppose I now go to the infinite Hotel Natura and I say, I would like to have a room. What is the receptionist going to tell me? Sure, all the rooms are booked, but I do have a room for you. He goes to every guest and say, well, guest number 1, move. So guest in room 0, move to room 1. Guest in room 1, move to room 2. Guest in room 2, move to room 3. Guest in room 3, move to room 4. Everybody can move. There is always a next room. And now look, room 0 is empty. Yes, they have a room for me. So Luca goes into room 0. Okay, now the hotel is full again with me. But let's assume that all of the people who are in V101 now go to Hotel Natura. Let's assume that there are 40 of those. Rough guess. They all go and say, do you have room for us? We go there with a bus. What is the receptionist going to say? Does he have room for us? Sure, of course it does. It just repeats the same trick. It just says, okay, Luca, you were at room 0. There are 40 new guys. Move to room 41. The guy from room 1 moves to room 42, and so on. And now 40 rooms are free. Fantastic. But let's make it worse. Now, the Infinite Hotel Natura is all full. And there is a bus with infinitely many people coming on. This bus has first passenger, second passenger, third passenger. There are countably infinity of people on that bus. Hotel Natura is infinitely full. It's full. Okay, so all the rooms are full. And there are infinitely many new people coming along. Countably infinitely many of them. What is the receptionist going to tell them? Sure, I got room for you. What does he do? He creates space for them. He says, you are a guy from room number 0, you stay at 0. Guy from room number 1, you go at 2. Guy from room number 2, you go to 4. Number 3, you go to 6. And you see the pattern. All the odd number rooms become free. So there is room for all of the guys on the bus. If it sounds strange to you, that's why infinite hotels don't exist. But if they existed, then, well, you could get a hell of a lot of tourists up in Iceland. But then you would have to feed them all, and that's another matter. As this is not bed and breakfast, it's only bed. There's not enough muesli in the world for all of these people. Okay? Cool. So I think your brains are roughly frying now. So this is probably a good time to take a break before we take the next step. And the next step, now you may guess, is to go up the number system one step and ask ourselves, is the set of real numbers countably infinite? And the answer would be revealed after the break. Well, revealed, not relieved. Revealed after the break.